And that new thing is how to determine empirical formulas from a mass percentage. And so in this case, we're talking about knowing that something is a certain percentage by mass of one element, then a certain percentage by mass of another element. And the way to do this is actually pretty straightforward. It's pretty simple, and you can remember it with the, so experimentally, this is how one usually does it. There exist books, shelves of books, that will tell you recipes to break up a particular compound into the elements that make it up. And you determine the mass of each element that you have in your compound. I have 3 grams of carbon, 2 grams of oxygen, stuff like that. And then using the molar mass of all these elements, that actually gives you an amount of each element, and then you reduce it to a final integer number ratio. So this is going to be a common link here in this and the next unit, that amount is the chemically relevant quantity. Things react atom to atom, molecule to molecule, or dozens to dozens, or more conveniently, moles to moles. But we don't have a way to directly determine moles experimentally, but we can determine mass experimentally very easily. And the molar mass of stuff is the link between those two. The thing that we want to know and the thing that we can determine easily. Now this process, breaking up into its elements, determine the mass, determine the amount, and determine the formula, that entire process can be summarized in a neat little rhyme. So say it with me, even if someone's around. Percent to mass, mass to mole, divide by small, multiply till whole. So say it again. And if during this quarantine you find that you need some time alone, some personal space, just find a corner of your house, crouch up into a fetal position, start rocking back and forth, and keep saying this. And I promise you, you will get your space. All right, so let's do this. First line, percent to mass. So I'm just going to run through an example. So there is a series of compounds that are made up of the elements boron and hydrogen. Back in the 50s, they were thought of, or they were used as potential high energy rocket fuels. They have a very high energy density. It turns out that they didn't work out so well. There were some other issues that made the engines blow up every once in a while. But what was really neat about these is when these things burn, the flame that would come out of the rockets was actually green and not the red, yellow, and orangey stuff you see now. And this was done, back in the 50s, where they were just starting to be able to have color photographs, and they're actually kind of weird looking. All right, so you've got one of these boranes, and it's been determined that by mass, it is 81.1% boron and 18.9% hydrogen. So how do we convert from percent to mass? It's really simple. Assume a 100-gram sample. And what's nice is what the actual sample that you used to make this determination was is utterly irrelevant. And with 100 grams, it makes the math for at least this step completely mindless. Which means that, if you had 100 grams at 81.1%, you know that 81.1 grams of it is boron, and that 18.9 grams of it is going to be hydrogen. So that's that. Second line, mass to mole. So all you're going to do is use the molar mass of all the elements to convert the mass from mole. So for example, I have 81.1 grams of boron. A mole of boron clocks in at 10.11 grams, so grams of boron cancel, and so this is going to give us 7.5 moles of boron. Do the same thing for all of the elements. In this case, it was just hydrogen that's left. So I've got 18.9 grams of hydrogen. Each mole of hydrogen clocks in at 1 gram. And that means that I've got 18.71 moles of hydrogen. Third line, divide by small. So here what you want to do is, get all of mine here, is whichever one was present in the smaller amount. In this case it was boron with the 7.5 moles. And then divide them all by that amount. So one of them, at least, should end up being 1, and that's the boron. And the other one here in this case is 2.5. And don't be too worried if they are not integers at this point, and in fact they usually aren't. Which brings us to the fourth line, multiply till whole. In which case, what you want to do, so these are the ratios that are going to be the subscripts in the empirical formula. But again, they need to be whole numbers. So what you want to do is multiply them by whatever factor makes them all integers. And also the important thing is that you need to do this to all of them. So here I've got a working empirical formula of B1 H2.5. So I want to multiply both of these by the same integer that makes both of these numbers integers themselves. And I will tell you that that number is usually 2 or 3 or like 5. And those are usually going to be the most common ones you're going to see, especially for examples that we do in a general chemistry class. And now, for example, so what number do I want to multiply these by? And hopefully you answered 2. So 2 times 1, 2, and then 2 times 2.5 gives us 5. Now these are engineered numbers, so sometimes these can be a little off. It might be like 2.48 or like 2.52 or something like that. But usually, you know, so if one of these is like 2.33, that would mean that you want to multiply that by 3. If it ends in 0.5, multiply it by 2. And those are actually the most common ones you'll see. So that means that the proper empirical formula of our borane rocket fuel is B2H5. But that is all it is. That's the empirical formula. How could we determine what the molecular formula is? Remember, for a lot of these compounds, those two are not the same. And the answer, I'm just working with this. And here's how you get that answer, by doing a different experiment. So the idea is that, you know, it could be, you know, the molecular formula could be B2H5, or it could be any multiple of that that gives you the same ratio. So it could also be B2H4, or B6H15, or B8H20 for that matter. So there are devices that are called mass spectrometers that actually measure the mass of individual molecules. And now, in many cases, it doesn't tell you much more than that. It, you know, gives you no indication as to what the formula might be usually, but it does give you the overall mass. Now, if you have the empirical formula and that mass, you can figure it out. So let's say that this thing returned a molar mass of 27 grams per mole. Now, I will tell you that that means that the molar mass is one of these three. Which one is it? Well, that 27 grams per mole is consistent with B2H5. So two borons will have a mass of about 20 AMU, or a little more than that each. So they clock in at almost 11 AMU. So the two boron atoms will have a mass of about 22 AMU total and average. And the 5 hydrogens will tack on another 5 AMU, so that will give you an average mass of about 27 grams per mole. And so if it were, if it were any of these other ones, it would have a much larger or, different mass. So let's see if you can figure this out on your own. And if the molar mass had been reported to be 81 grams per mole, what's the molecular formula? And that molecular formula is consistent with the formula B2H6, because that would add up to 81 grams per mole. So the mass spectrometer just basically tells you the molar mass, but if you have the empirical formula as well, those two together can give you the molecular formula, and that's how you do it. If you want to practice, try this, azurite. So this is one of the minerals from which copper is mined and refined, and it contains the raw ore form contains the elements copper, carbon, hydrogen, and oxygen in these respective percentages by mass. So it's mostly copper and oxygen with a little bit of carbon and hydrogen in there. And go through that same process that we did with the boranes, except now you've got 4 elements to work through. And if you can do this, you should have no problem with any assignment, quiz, or exam question. So what do we got? So here's the answer. I'm just going to throw it out there. So that ends up having a formula of C3C2H2O8. Now, going back to the last unit with naming, this is actually what it is. It is copper, 3 of them, 3 copper plus 2s. Ignore the fact that it says 2, it should say 3. And it is combined with 2 carbonate ions and 2 hydroxide ions. So let me fix my mistake here. 3.